Okay, in this next episode, we're going to continue with force and motion, but we're going to get more into the electrical and away from the plumbing. But we're still going to make the comparison between gravity, flow, resistance, voltage, resistance, and electron flow. We're still going to work with that comparison. When we're done with this one, then in the next one, I think this is episode 7, I can't remember, but in the next one we're going to go back to Tinkercad and we're going to look more at voltage, resistance, and current, because there's a direct mathematical relationship there between voltage, current, and resistance. And you can calculate exactly what a circuit's going to do based on how much voltage you have and how much resistance you have. Because remember, the current is a result of the pressure against the resistance. So here's your pressure, here's the resistance, and you get a certain amount of flow. If you've got more resistance, you get less flow. If you got less resistance, you get more flow. You'll get the point. So at the end of this one, in the next episode, we're going to go to Ohm's law. OHM, Ohm's law. Thank you. Let's watch this.
So you notice on our regulator here, there's 2 flange mounts. One on the right that has an arrow coming in from the tower, and one on the left that's going out to the residence. So this could be mounted horizontal, and the pipe comes down from the tower, takes a 90, goes in, comes out the residence side and goes down to your house. Or it could be mounted vertical. It doesn't matter, because this device is not dependent upon gravity. It's dependent upon pressure. And there's 2 pressures at work here. One of them is the spring, which you can see kind of a cutaway view there, and maybe you didn't recognize that right away if you're not used to looking at this kind of a diagram. But in the upper portion of this regulator, you see the cutaway view of a coil spring. At the top of that coil spring, you see a threaded bolt with a lock nut, so you can take and screw that bolt in, and that compresses the spring. Now, what you may not see quite as easily is that spring pressure is pushing down because it's pushing against the outside of the casing. It's pushing straight down. If you follow the rod down, you'll see a clapper. It's a valve where you see the little arrow representing the water that comes in from the tower, goes down and then comes back up on the other side of that mechanism to go out the residence. So the water has to get through that valve right there, and the spring is forcing the valve open. So this diagram is drawn with the water pressure from the tower. Well, it's drawn with the valve closed. So let's continue. Okay, this is the pinch right here. So if you were going to control water flow through a garden hose, what do? You pinch it, right? You either fold it so it's completely pinched off, and then you walk over to where you want to continue, then you release it and you get your flow grin. Or if you're trying to keep the water from not coming out so hard and washing away, we'll say, the soil out of the pot that you want to add water to for your outdoor flowers, you kind of semi-pinch the hose to reduce the flow. That's basically what this regulator does. But what the regulator does is it pits the water pressure from the residence. In other words, the water comes down from the tower, flows through this valve, it fills up the pipe between the regulator and your house, and as it fills up, the water pressure backs up from the house into this regulator, and it pushes against that spring to close the valve. So when you open a valve in your house, the water starts to flow out of the residence side of this regulator, the pressure drops, the spring takes over and forces open the valve, the tower sends more water in, and so it's always a balance between the backed up water pressure from your house and the residence side of this up against the spring and the spring tension. So the adjustment of the spring determines how much water pressure you're going to get. It's a regulator. It regulates pressure. So there's the spring, and the spring is pushing down to open the valve. The water pressure from the house is pushing back to close it. And when they're equal, then the valve is going to be closed. So this is adjusted, the bolt on the top of this regulator is adjusted until the water gauge at your home entrance equals roughly 45-50 pounds PSI. That's how you adjust these regulators. So if we go back to our residential system and we install one of these regulators in all 4 downcomers and we adjust them each to 50 PSI, then all 4 residences will always have 50 PSI, unless of course the tank up above goes empty. Typically, these regulators are sized or adjusted so when the tank is almost empty, you still have enough force on top of the regulator to be greater than the force coming back from the house. So in other words, if the force from the tank got lower than 50 PSI, then all the regulators would just be wide open. And actually that's what happens if you let that reservoir up in the water tower go empty. The regulators are wide open because there isn't enough force from the houses coming back because you're draining away the water. It's time now to make the transition from gravity and water flow to voltage and current and electrical resistance. Electrical current would be analogous to flow. So gravity gave us water pressure, which gave us flow, opposed by the resistance. Electrical current is the motion or the movement of electrons through a conductor from atom to atom. One thing I did not emphasize before, and it's not that important, is that if you wanted to, you could look at the free electrons, 1 per copper atom. You could look at those kind of as a pipe full of ping pong balls, all tight, pushing up against each other. If you have a pipe 1 mile long and its inside diameter is exactly the size of a ping pong ball, just a hair larger to allow the ping pong balls to move easily. If you force another ping pong ball into one end of the pipe, one's going to pop out of the other end, but not the one you forced in, the one that's closest to the other end. Because remember, electrons are negative and they repel each other. So if I place 1 extra electron in one end of the wire, that bumps all of the free electrons over 1 atom all the way down through the conductor, and 1 electron pops out the other end. Now remember, in order to get current to flow, electrical current, electron flow, I need to put a negative charge on one end and a positive charge on the other. So remember, the negative charge is an excess of electrons and the positive charge is a deficiency. So if I put that charge across the conductor, one of the excess electrons is forced into one end of the wire and the positive charge on the other end pulls out 1 electron. So the number of electrons in the copper wire stays consistent as you're forcing electron flow through the wire. So flow is electrical current. The force that we use for water flow is gravity, or pounds per square inch water column, head, however you want to describe it. The force for electrical current is voltage. It's measured in volts, and it's just referred to in general as voltage, but it's really EMF, electromotive force. It's the electrical force that motivates the electrons to move. And the greater the voltage, in other words, the greater the potential force across that conductor, negative on one end, positive on the other, the more excess electrons and the more deficiency of electrons you have, the stronger the pull to pull those electrons traveling along the copper wire. And of course, resistance is resistance. In a water pipe, the resistance was the friction on the sides of the pipe. And the reason a smaller diameter pipe has more resistance than a larger is that when you apply force to push water through the pipe, that force is also against the sides of the pipe. So you're actually pressing the water that flows along the sides of the pipe tighter and tighter against the side of the pipe. That increases friction. So the greater the force that you have, the more it pushes against the side of the pipe, and basically it dissipates in the form of heat. You wouldn't believe that, but water flowing through a pipe does heat up the pipe, but not to the touch. It's just a fraction of a degree. Electrical current, the resistance to current flow from voltage, is measured in ohms, and we're not going to get into the math, but as I explained that copper is a good conductor, silver is better, and gold is even better yet. Therefore, there are conductors that the electrons are more easily moved than other conductors. Some materials, you can't move the electrons at all under normal voltage pressure. They are insulators. However, if you apply a high enough charge, a strong enough force, just like if you have a high enough water force, it will burst open and destroy the system, but there will be flow. So an electrical system, and a good example would be in a thunderstorm, if a bolt of lightning hits the power lines and sends a surge into your house, the plastic and rubber insulation on all of the conductors running through your home have a rating usually of 600 volts. If that voltage is exceeded, and they measure the ability of a material to insulate electrically, they call it a dielectric strength. So if you exceed that dielectric strength, in other words, you have 10,000 volts that comes in, and you have insulation that's good for 600 volts, you're going to get electrical conduction through that insulation. But it's going to destroy the insulation because it is literally ripping electrons off of the atoms with such a violent force that it's going to destroy the material. So there are other materials that are called semiconductors, and they allow electrical conduction, but not as freely as copper, silver, or gold. So there are a variety of ways to control electrical flow. You can control it with a field. If a magnetic field, which is made up of the magnetic fields of many electrons, if that magnetic field can induce a current to go one way, another magnetic field can inhibit it from going that direction and control it. So you can control electron flow with a magnetic field that's trying to push it in the opposite direction. So the end result, or the flow, is going to be a balance between the two forces. One's pushing it one way and one's pushing it the other. The one that's greatest is going to dominate, and the difference will be reflected in the actual current flow. So as you increase and decrease one of those forces, the current flow increases and decreases. Let's step up to another level of analysis of what's going on here. In electrical circuits, in order to have flow, in other words, in an electrical circuit where you want to have flow, you want a complete circuit. And that complete circuit is the path in which has been designed to carry the electrical flow. In the case of our water system, the water pumps up to the tank, the reservoir, and then gravity carries it down through the house into the waste system, into the soil, into the aquifer, and it's reavailable to pump back up again. Now, just as the water molecules that come out of your waistline don't necessarily end up going back through the pump to your tank, they are available throughout the world. Electrons are available basically through the ground. And if you've ever heard that term, well, it wasn't grounded, or it needs a ground connection. We have a phrase that we've said for years: ground is ground the world around. A lot of electrical systems actually use the ground as one part of the electrical path to complete the circuit. So if you grab one side of the 115 volt AC line in one of your outlets, and your feet are standing on a wet spot on the ground, you might get electrocuted because electricity will flow through the ground. Remember, the ground's made up of many elements, some of which are conductors. Now, not all ground is a good conductor. Sand, dry sand especially, is very poor. But anyway, you see the idea of a complete circuit. And this is the complete circuit that we've been working with so far. And there's something called circuit theory. The theory of accomplishing work by routing electrons, fluids, or any other matter through loops: water, natural gas, petroleum, electrical, hydraulic, or pneumatic. Now, normally in a pneumatic circuit, it resembles more the residential water supply than the rest of them do, because with a pneumatic system, you pump air out of the atmosphere into a storage tank and until it gets up to a certain pressure, and then you use that air pressure to and you control it with pneumatic valves to get cylinders to extend and retract. Normally, once you've used the air to push a cylinder forward, it exhausts out into the atmosphere, which would be like the aquifer, only for air. So circuit theory is the study of all these different kinds of complete circuits. So how do we control the flow of water through the residence? Well, we start with a float switch in the tank. And down the Dominican Republic, my float switch that I put in my tank is actually just a bulb on the end of a conductor that floats freely on the surface of the water, and it works on attitude and gravity. So as the water lowers in the tank, the float starts to angle down, and when it gets far enough down, then gravity carries the weight inside of the switch bulb to close the switch. And then, of course, it turns on the pump, the water pumps back up, it starts floating back up until it's above level and tips the other direction, the other attitude in the opposite direction, and the weight slips the other way and opens the switch. So here we have a float switch, and there are other ways you could do this. You could do this with a float valve, where the float actually closes a valve and fights the pressure from the pump. Now, that's not a good idea because you don't want the pump running. So we use a float switch. Then we have a pressure regulator that regulates the amount of pressure that's actually felt at the residence. That gives you nice, consistent use of the water. And then, of course, you control water flow with valves. Or you have a valve in your refrigerator that controls water flowing into the little ice cube cavities. The water in your hot water heater, that's strictly water pressure. So, and that's good because you want the water pressure from the tower to be felt all the way through the hot water system to your hot water valves on your sinks and shower. That way you've got water pressure for the hot water. So it's the cold water pushing on the hot water in the hot water tank that pushes out the hot water for you to use. This is an electrical circuit, and we're going to draw some direct comparisons between the public utility freshwater system and this electrical system. Instead of a water pump pumping water from the aquifer up into the storage system, we have an AC power source from the public grid. In other words, the pole outside of your house comes in through your service entrance, goes through your service box downstairs. You call it the breaker box. And in there are a number of circuit interrupting devices that if you were to draw too much current, they would pop open and not allow your house to be burned down. We also have a switch to complete this circuit. So we had a float switch in the tank that turned off the pump if it was full. So this switch, we basically turn on the whole circuit with this. So it is slightly different. But we do need a way to turn this entire circuit on and off. Then we have a battery to store the electrical energy. So the electron flow in this case actually is going from the AC power source down through the wire and up into the bottom of this cell, and then coming out the top are electrons going back to the AC power source. So we're charging up the negative side of the battery with electrons, and we're removing electrons from the positive side of the battery. So we're adding electrons to the negative side and removing them from the positive side. They're not the same electrons. So what we're doing is we're creating a charge, an electrostatic charge between the outer shell of this cell, which is negative, and the inner pole, that cathode or graphite rod in the middle, is now missing electrons, so it's positive. And there's another little symbol up there by the switch that looks like an arrow. That's actually a diode or a rectifier, because we have an AC source, meaning the current is going back and forth. It's switching direction 120 times a second, which gives you 60 hertz, 60 cycles. A complete cycle is current goes one way, then goes the other. That's one cycle. So you get 60 of those a second, but we only want current to flow one way through that battery, and that's to charge it. That's why we have that diode in there. Now we also have a switch to complete the circuit from the AC power source to the LED or from the battery to the LED. We have a light emitting diode, which is, we're not going to get into the discussion of how the light emitting diode works, but it basically is a conductor, but it has some semiconductor material in there that gives off light instead of heat. And then of course copper wire is connecting everything. So remember, our water system had a charging system and it had storage. So we would use the charging system to charge the battery or to directly power the light. And basically the end result here, or the desired result, is flow, electron flow. So flow is determined by how much force and how much resistance that we have. In the case of electrical circuit, we're going to call it voltage, electrical current, and resistance. So the more voltage, the more electrical current for the same resistance. Now, if the switches are open, that is an infinite amount of resistance. There's going to be absolutely zero current flow, electron flow, through an open switch, because electrons cannot jump across the air. Now, that's not totally true, and I will show you in a minute what I mean by that. But for the voltage that's supplied by this cell, when fully charged, gives you about 1.5 volts, so 1.5 volts. At 1.5 volts, that's not enough pressure to make electrons jump across the air gap of an open switch. Now, I said that the electrons can't jump across the air in an open switch, but I said that wasn't always true, but it was true in a circuit where you're limited to 1.5 volt. Let's take a couple other situations here. The first one that everyone has experienced, and that is where you have static electricity build up on your body. Now, I'm showing your finger very close to the doorknob, and the red cloud there is kind of the electrostatic field between the electrons, the excess of electrons in the doorknob, and the deficiency of electrons in your hand. It could be the other way around, just depends on how you generate the static electricity. But keep in mind, when you were 10 feet from the door, there was an electrostatic field that extended from your body out to everything around you. However, the field is going to be strongest between you and a source of the opposite charge. Remember, I said ground is ground the world around. So this doorknob really isn't ground, it's probably neutral. But neutral is still either less positive or less negative than what your body is. As you draw near to that doorknob, that electrostatic field intensifies between the positive and negative charges. And the closer you get to the doorknob, the stronger the field becomes. The voltage actually increases. So you've got two things working here. The voltage is increasing, the field strength is increasing, and there's less and less air molecules between your skin and the doorknob. And when you get close enough, you get an arc, and that arc discharges the difference in potential between your body and that doorknob. So this is an example where electrons do jump across air. Now, what I do, if I know I'm going to get shocked, I walk up and I slap the doorknob. So the pain of hitting the doorknob with my hand is greater than the sensation of the arc. I don't like getting shocked. As an electrical engineer, I've gotten some pretty hard hits over the years. None in the last 30 years, probably, because when you're young, you do some real stupid things. Got to tell you a story real quick. When I was in the Marine Corps, my primary MOS was microwave radio relay technician, which means I was a grunt, a ground pounder. But when I wasn't fighting, I was repairing microwave equipment with, microwave waveguides, directional antennas, everything. But when I was in class learning about radios, we had these AM radios. They're really for military use, not for civilian use. But you could tune in local stations. So I'm sitting there, and I'm supposed to be doing one thing, but what I did is I took one of my meter leads, I stuck it in the coax output for the antenna, and then stuck the other end behind my ear and under the headset. So my body was basically an antenna to improve the reception. I'm sitting there jamming out, listening to tunes, right? So here comes the instructor. Remember, I'm a private. And here comes this gunnery sergeant, big old nasty, hairy, gnarly gunnery sergeant who's teaching the class. So I didn't want to look like I was goofing off, so I quick grabbed the other end of that lead out of the coax connector for the antenna, and I went over, and without thinking, I put it on the B plus cap on one of the power amplifiers that had like 200 volts on it, and I got 200 volts through my ear. So that was a hard shock, but it was my own stupidity. It wasn't static electricity either. It was a continuous current. Okay, here's our circuit. We have a switch closed and a switch open. So basically we have the circuit completed for charging the battery or charging up the storage. So remember, this is an AC source. So in one polarity, electrons come out of the AC source, come in the bottom of the cell, replacing the electrons that have been dissipated in the outer shell of this cell. Electrons come out of the center rod, the graphite rod, the cathode, and go to the AC supply. When that half cycle is completed, and then we see the other direction, notice the negatives on the top, now positive on the bottom of the AC supply, that diode will not allow current to flow in that direction. If it did, then electrons coming out of the AC supply would go up and down in the positive side of the battery, thereby discharging the battery. So we want those positive charges on that center rod, that graphite rod. If you ran electrons in there, that would complete them and you wouldn't have any voltage to work with. So if you're going to charge up a battery, you need direct current, not alternating current. And you can get direct current from alternating current by putting in a rectifier, a diode, which will obstruct one half cycle and only allow current to flow in one direction. So the battery is charged up. Now we open the charging circuit, and now here you go with your charged up battery, and you're going to operate something. Close the switch. The battery's fully charged. Electrons flow out of the bottom of the cell, go around up through the LED, illuminating the LED, and then the electrons go back to the positive side of the cell. But the whole time this is happening, you're depleting the excess of electrons off of the outside shell and depleting the positive charges in the center rod. So eventually the battery will die and your LED will no longer be illuminated. If we add more circuits to this cell, basically we have 6 LEDs now, and we have 6 individual switches, and they are in parallel. So all 6 of these load circuits with their 6 individual switches are in parallel with the batteries. The battery is 1.5 volts. So if we turn on one LED, then we have 1.5 volts across one LED. But remember back to our storage system when it was a water tank supplying water to houses. The more houses that are drawing water, the faster you deplete the water level in the tank. If we add 2 batteries in series, voltage adds in series. So now we have 2 1.5 volt cells, or a total of 3 volts. So we've got twice the voltage, which means the LEDs will illuminate twice as bright. Close the switch, current flows, and we closed all the switches, so they're all burning brighter than they did at 1.5 volts. But keep in mind, because we're drawing 6 times the current for 6 times the LEDs, the resistance is also increased, so we don't have 6 times the current. But we do have more current with 2 batteries in series. 2 cells in series gives us 3 volts. If we put them in parallel, we still only have 1.5 volt, but we have, this would be, if I back up here a second, this is a higher water tower, higher voltage. This is the same height water tower as one battery, but because we've got 2, that's like having a water tower that's twice as big around, but the water's still the same height over your house. So you didn't increase the height of the water column, just the total amount of water available in the reservoir to discharge down the downcomer to your house. So in this configuration, 2 batteries or 2 cells in series are going to give you twice the current, roughly twice the current, and the LEDs are going to burn twice as bright, but still no longer than they would have burned at half the brightness for one cell. With two cells, they're going to burn at the normal, they're going to illuminate at the normal level, but for twice as long because there's more capacity.
What you just saw should have lined up with what you saw earlier when we were using Tinkercad and we were working with batteries and light bulbs, LED, and a switch. So it should be kind of meshing together now with the hands-on things we've shown you. So in the next episode, next video, we're going to go back to Tinkercad and we're going to actually exercise some very small equations that you have, say, a voltage and current, and you want to know how much resistance there is based on the voltage that you applied and how much current flow you got, or vice versa. You can calculate any one of the three if you know the other two. So that's it for this episode. See you in the next one. Thank you.